dl along this path, that is dl along this path. Now, according to Coulomb's law, we know that the force extracted on the charge q in an electrostatic field E, according to Coulomb's law, the force extracted on this charge q, that is given by capital F is equals to q into E, according to Coulomb's law. Right? Now, if this point charge is moved from point A to point B, so there is a displacement of the charge occur, right? So if there is a displacement of a charge with against a force, electrostatic force F, so there must be create a work done, right? And this work done is given by dW, and if the displacement is denoted by di, differential displacement is denoted by di, then the work done dW is equals to minus of dF dot di. F dot di. F is the force and I is the di is the differential displacement. Right? Now, according to Coulomb's law, we know that Q is equals to F is equals to Q into E. Because this charge Q is displaced with against the electrostatic field E. That's why force is equals to Q into E. So, dW we further write as is equals to minus QE dot DI, right? QE dot DI, the putting the value of F in this equation. And one thing remember, this negative sign indicates the work done by an external agent or work done by an external charge. Okay, and thus the work done or the potential energy that is generated when this charge Q is moved from A to B. Charge Q is moved from A to B. Right? That is equals to if we integrate this dW and in this equation, so integration of dW is equals to integration of QE dot Q into E DI, right? So integration of dW is equals to W, that is equals to Q is a constant, and this electric field is extended to A to B from, because A is the initial point and B is the final point. So that's why W is equals to minus of Q integration of A to B E dot DI, right? So this equation number 153 basically represent the work done of the point charge Q if the point charge Q is moved from position A to position B, right? Now if we divide this equation by Q, if we divide this equation 153 by Q, that represents the potential energy per unit charge. Okay, if we divided this equation number 153, that means W is equals to minus Q integration of A to B E dot DI, then it represents the potential energy per unit charge, right? Per unit charge. Okay, so the quantity that the potential energy per unit charge is denoted by VAB, right? And this VAB is the potential difference, of A to B, right? So the potential electric potential difference that is represented by the potential energy per unit charge. So VAB that is equals to QW by Q, right? That is equals to minus of integration of A to B, E dot DI, right? Okay, so VAB represents the electric potential difference of a point from if a point charge Q move from A position to B position. Okay, equation number 154. Equation number 154 that represents the electric potential difference between A and B in the electrostatic field E. Okay. Now, one thing remember that uh, uh, this potential difference VAB have the following uh, um, um, characteristics. Okay, it has the following characteristics. Which characteristics? Okay, first characteristics is that the uh, in this potential difference, when you determine the electric potential difference across along VAB between two points, you have to take A point as an initial point of the charge and B point is the final point of the charge. That's why VAB is equals to integration over A to B E dot DI. Integration over A to B E dot DI. That means when you the potential difference between any 2 points, so lower limit will be the initial point of the charge and upper limit is the final point of the charge. That means A is the initial point of the position of the point charge and B is the final point of the position of the point charge. Okay, it is the first characteristics of the potential difference. Okay, now if VAB uh, determine the electric potential VAB in negative term, that represent that this is a loss of potential energy if we move a point charge from A to B, right? If the potential difference is negative, that means that there is a loss of potential energy when the point charge Q move from A to B, right? Okay, and whenever the VAB whose value generated in positive term, okay, that means that there is a gain of potential energy when the point charge is moved from A to B. So negative sign indicate there is a loss of potential energy if we move the point from one position to another position, and VAB positive indication, positive term that represent there is a gain of potential energy in the movement of point A to point B. Okay, so this is the second characteristics of the potential difference. Okay, and another important characteristic is that when you move along a path, when you move a potential from A to B along any path, because along any path there is no limitation over there. So VAB is independent of the path taken. This is the third characteristics of the potential difference. Okay, that means VAB is the independent of the path taken. That means you have to move any path in A to B, but there is no relation between the path taken of the VAB. That means that if uh, A and B, if A is the point and B is the another point, if the vector locations is A point and B point are different in 3 cases or 4 cases, but the potential energy is independent of the path taken. Okay, that means the Q point charge which moved from path A to path B or position A to position B. Okay, the path is independent. So Q is moved in any path from point A to point B. Okay, then fourth characteristics is that uh, the electric potential difference VAB, okay, that is measured in joule per coulomb, right? It is joule per coulomb because we know that electric potential difference is the given by the potential energy per unit charge. Potential energy per unit charge W by Q. That's why it is unit is joule per coulomb or SI unit is volt. Okay. Now another equations. Now if VAB, we know that VAB that is equals to minus of integration over A to B integration over A to B E dot DI. Okay. Now according to Coulomb's law of point charge, we already discussed and already proved that the E is equals to electric field E is equals to Q by 4 pi epsilon naught R square into AR. Okay, we have already proved that E is equals to Q by 4 pi epsilon naught R square into AR. Now we put the value of E in this equation. Okay, right? Right? Now, so E is equals to Q by 4 pi epsilon naught R square AR dr dot AR. Now, AR dot AR, that if we uh, dot product of AR dot AR, that is equals to 1, right? Okay. Now, the position vector or position vector of A, position vector of A, that is that the distance from the origin is small ra, and distance of B point from that origin, that is RB. So if we take reference point O, that means O as a taken as a reference point. So this point charge A moves along this path to RA distance to RB distance. Okay, RA distance to RB distance. That's why this equation become VAB is equals to minus of small integration over small RA to small RB Q divided by 4 pi epsilon naught R square AR dot dr AR. Right. Now 4 pi epsilon naught that is constant. So it is out of the integration. So VAB is equals to Q by 4 pi epsilon naught. Now we integration over RA to RB, integration over RA to RB 1 by R square dr, right? 1 by R square dr. So it will be after integration 1 by 1 minus 1 by R, right? Minus 1 by R, and this minus already A. So after integration it will be 1 by small r, whose upper limit is RB and lower limit is RA. So if we put the upper limit to lower limit in this integration, so equation that means VAB is equals to Q by 4 pi epsilon 1 by RB minus 1 by RA. Okay, that is represent the equation number 155. Right? Another, we know that uh, if we taken a potential difference between 2 points, it will be also know that the potential difference is the potential difference of the B point. VAB is represent, we also know that VAB, it is represent as VB minus of VA. That means potential of VB minus potential of VA. Okay, where VB is the potential of B and this is VA. This is VA. VA is the potential of A point. Now, thus the potential difference VAB uh, may be calculated uh, with a concept that the A point is situated at the infinity region, or A point is situated at a distance of infinity with respect to the reference point. Okay, that means we assume this A point is situated at infinity from origin. That means this RA tends to infinity. This RA tends to infinity, and we move from infinity point to a point whose distance is RB, and RB is tends to small r, right? Okay, RB is tends to small r, and RA is tends to infinity, right? Okay, so this equation become, so if a point charge, we assume the potential at infinity, the and it is you know that the potential at infinite point whose potential is 0, right? Whose potential is 0. Okay, that's why when we uh, define any potential 5 volt, 6 volt, 7 volt, 10 volt, that will be know that it is uh, with respect to ground potential, right? With respect to ground potential, if we draw a 5 volt, so if we connect positive terminal of the battery is equal to 5, negative terminal is the 0 potential. So 5 volt is defined with respect to a ground potential, right? And ground potential whose value of the potential is equals to 0. Okay, and here we taken at infinite distance, ra tends, if ra tends to infinity, the potential of the va point is equals to 0. Okay, and the another point, the B point which tends to R, right? If which tends to R, so that's the potential at any point, any point that tends to RB tends to R, and RA tends to infinity. Why RA taken RA tends to infinity? Because we know that the potential at infinite distance is equal to 0. Okay, so if we modify this equation, number 155, right? If we modify this equation 155 and RB, that tends to RB tends to R and RA tends to infinity. Okay, then this will give, that means if RA tends to infinite, the 1 by infinity, that portion will be 0. Okay, Okay, and if RB tends to small r, so that portion will be 1 by r. So this equation 55 is remodified to the equation V is equals to Q divided by 4 pi epsilon r. So that equation number 55, that gives the potential of the point B of the point Q if a point Q that moved from a infinite distance point touch to a distance of r. Okay, and this distance is treated as a infinite with respect to that point O. Okay, that means this array, that means a point is situated at the infinite distance from O, and the B point is situated at the distance of R. That means this RB tends to R and RA tends to infinity, then the potential difference, okay, V is denoted by Q by 4 pi epsilon naught into R. Okay, that is this 156 is denoted the potential difference. Okay, potential difference or potential at any point which is situated, one in is infinity and another is the distance to r. Okay, this is very important relation of potential difference. Okay, got my points? বোঝা গেছে?
Yes, sir.
Okay, so you have to uh, we have to determine this equation from this way. Okay, you have to develop this equation from this way, from this figure. Okay, now then again, the potential at any point, the potential at any point is the potential difference at that point and a chosen point at which potential is zero. Got my point? That means if we choose any point in a electrostatic field and we determine the potential at that point, so this will be the potential difference of between that point and another reference point which is situated in infinite distance whose potential is zero. That is the concept. So that's why it is called the potential at any point is the potential difference between that point and a chosen point whose chosen point is situated in infinite distance and whose potential is zero. Okay, so in other words, okay, the potential at a distance r from a point charge is denoted as a work done per unit charge by an external agent or external charge, that is transfer or external charge or test charge. It is called test charge. It is transferring from infinite distance to that point. Okay, so that's why it is also denoted as V, capital V is equals to minus of integration over infinity to r E dot di, right? E dot di. V, this is the integration form of the potential difference, that is V is equals to uh, uh, the minus of integration over integration over infinity to r E dot di, right? Okay, now if the point charge q, if the point charge q, the equation That is, we know that V is equals to Q by 4 pi epsilon naught R. Now, if this point charge is not located at the origin, it is located another point whose vector's notation, whose vector distance is r dot, right? If a point charge q in the equation v is equals to v is equals to 4 pi epsilon r, that gives the potential difference with respect to reference point, that is origin. But if this point is do not situated at origin, it is situated in a vector whose value is r dot, okay, r dot, and is r dot in Cartesian coordinate form, it is x y z form. Spherical coordinate, it is r theta rho phi z form, and is cylindrical coordinate is rho phi z form, and in uh, so cylindrical spherical coordinate r theta form. Okay, then this potential difference, if the point is not situated in the origin, then that will be given by v of r. V of r is equals to q by this situation. This equation is modified to q by 4 pi epsilon naught mod of r minus r dot. These are whose vector location at origin, and r dot whose vector location is the another point in the Cartesian field. So the potential at any point which is whose vector position vector is r dot, then this equation is given by v of r. V of r is equals to q by 4 pi epsilon naught mod of r minus r dot, right? Okay. Now this equation 158 is represent is a one with respect to one point charge. Now if there are n numbers of point charge are located in the position vector of r1 r2 dot 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 rn, that means q1 whose position vector is r1, q2 whose position vector is r2, q3 whose position vector is r3, qn whose position vector is rn. Then the potential at r point, that is given by v of r is equals to the uh, potential of each, or addition of the potential of each point. Okay, so v of r that is equal to q divided by 4 pi epsilon naught mod of r minus r1 plus q2 4 pi epsilon naught mod of r minus r2 plus q3 4 pi epsilon naught mod of r minus r3 dot 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 qn 4 pi epsilon naught mod of r minus rn. Now, if we take summation of this equation and uh, mm, uh, equating in a generalized form, okay, so v of r is equals to 1 by 4 pi epsilon naught summation of k is equals to 1 to n qk mod of r minus rk. Okay, so that equation is the potential of a of of point charge of n numbers of points, okay. V of r is equals to 1 by 4 pi epsilon naught summation of k is equals to 1 to n qk divided by r minus rk. That is the potential of the n numbers of point charge is situated in the different vector location from r1, r2, r3 dot 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 rn, right? Okay. Now Got my point? Now, if for continuous charge distribution, okay, for continuous charge distribution, okay, if there is a this equation for point charge, but if it is a line charge, it is a surface charge, or it is a volume charge, then this equation will be converted to another equation. Okay, which equation? For line charge, mind it, for continuous charge distribution, for continuous charge distribution, okay, qk, this qk, okay, this qk is replaced continuous charge distribution, but point charge, this is a discontinuous charge distribution, because this q point is situated, that means q1, q2, q3, q4 dot 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 qn, these are not situated along the line. Okay, this charge is situated haphazardly in the electric field. That means uh, this this r1, this q1 is situated at r1 vector position, this r1 vector position, q2 is situated r2 vector position, q3 situated in the r3 vector position. Similarly, qn is situated in the rn vector position, right? Okay, so this r1, this position vector r1, r2, r3 dot 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 rn, these are not in along the line or along the surface or along the volume. Okay, these point charge are situated haphazardly in the electric field. Okay, then the point charge equation will be V of r is equals to 1 by 4 pi epsilon naught summation of k is equals to 1 to n qk mod of r minus rk. This is for the point charge. Okay. Now, if for continuous charge distribution, that means if we take this point charge q1, q2, q3 dot 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 along a line, along a straight line, and continuous charge distribution, that means along a straight line at all points the charge distribution is equal, right? Or along a surface, okay, along a surface, that means if we take a surface whose charge distribution along all points of the surface is equal, or along a volume, okay, along a volume, that means if we take a point, any point in the volume, any point of the volume, the volume charge distribution is same. In that case, qk, that means the point charges, is replaced by the charge, the charge density. That means line charge density into dl, volume surface charge density into ds, and volume charge density dv. So qk is replaced by ql dl for line charge, qs ds for surface charge, and qv dv for the volume charge. So if we replace this qk, so v of r, this this is for continuous charge distribution. One thing remember, for continuous charge distribution, so for continuous charge distribution, this summation is replaced by integration. Mind it, this continuous charge distribution summation is replaced by integration. But in discontinuous charge distribution, okay, discontinuous charge distribution, okay, it is denoted by summation. Okay, that's why this qk is replaced by line charge densities, volume surface charge densities, and volume charge density with respect to line charge, surface charge, and volume charge. And this summation is replaced by integration, because integration represent continuous charge distribution, summation represent discrete charge distribution. Okay, that's why this equation number 159, that is uh, converted to V of R, that is converted to V of R is equals to 1 by 4 pi epsilon naught line integration of rho L R of R dot rho L R dot of D L dot divided by R minus R dot mod. It is for line charge, and for volume charge the equation is replaced by V of R is equals to 1 by 4 pi epsilon naught surface integral of rho S R dot ds dot divided by R mod of R minus R dot. And for volume charge, okay, for volume charge it is represented as 1 by 4 pi epsilon naught volume integration of rho v d r dot dv dot divided by r minus r dot for the volume charge. Okay, so for discontinuous charge distribution, the electric potential of V of R is represented by this equation. But if it is a continuous charge distribution, this equation is replaced by integration and qk. That means the point charge is replaced by charge density. Point charge is represented by charge density. For line charge, it is replaced by line charge densities. For surface charge, it is replaced by surface charge densities, and volume charge, it is replaced by volume charge densities. Okay, বোঝা গেছে? Got my points? আচ্ছা, let we move to one example in electric potential. Okay, now 2 point charges, ঠিক আছে, 2 point charges, one whose value, one's value is minus 4 microcoulomb, which is situated at a vector location 2, -1, 3. Okay, and another point charge q, another point charge q2, whose value is equals to 5 microcoulomb, that is situated at the vector location 0, 4 and -2. So if you see this, 2 point charges are located in 2 different vector locations. That means, and the vector location are not uniform. First charge whose point vector which is situated at x is equal to 2, y is equal to -1 and z is equals to 3 location, and second point charge q2, that whose value is equal to 5 microcoulomb, which is situated at x is equal to 0, y is equal to 4 and z is equal to -2. So this 2 point charge is located in different location. Okay, different location of the Cartesian field. Okay, now we have to calculate the potential. We have to calculate the potential at a point, the reference point, which is not in the origin 0, 0, 0, which is situated in the 0, 1, 0, 0, 1, 0, 1. That means x is equal to 1, y is equal to 0 and z is equal to 1 position. So we have to calculate the potential difference at that point 0, 1, 0, 1 with respect to this 2 point charge. Okay, this 2 point charge which is situated in this equation, right? And we assume the zero potential at infinity. Okay, one thing remember, that when you calculate the electric potential, okay, you have to move a point charge q from infinite point to that point, infinite point to that point, right? An infinite point to that point with respect to this reference point, and then we calculate the total electric potential created or total electric potential generated due to movement of this point charge. Okay, now the value of q1, the value of q1, that is equals to 4 microcoulomb, that is equal to 4 into 10 to the power minus 6 coulomb. Q2 is equals to 5 microcoulomb, that is 5 into 10 to the power minus 6 coulomb, right? Okay, now according to this discontinuous point charges equation, if we take this equation, V of r is equals to 1 by 4 pi epsilon naught summation over k is equals to 1 to 2, because we have to move 2 point charges. That's why we have taken k is equal to 1 to 2 qk divided by r minus rk, right? So if we uh, extract this summation, so this will be V of r is equals to q1 divided by 4 pi epsilon naught mod of r minus r1 plus q2, okay, q2 4 pi epsilon naught r minus r2 plus c naught. This c naught is the reference infinite point charges value, okay, c naught. Now if we if we take the infinite distance, then the value of c is equals to 0, but it will be so in your equation, okay. So there will be given that infinite potential at infinity. That's why v of infinity is equals to 0. If v of infinity is equals to 0, we know that q is equal to cv, so c is equals to also 0, whose charge is also 0, right? Okay, now we determine this vector position, because q1, q2, 4 pi epsilon naught, these are all the known values, okay. The value of epsilon in the general cases, that is 10 to the power minus 9 divided by 36 pi, it is the general value. Now r minus r1 mod of r minus r1, that is equals to, this r is the vector location of the reference point, that means 1 0 1, okay. Now put this value 1 0 1 minus of the vector location of the q point, okay. So 2 minus 1 3. So now if we equate it, okay, so the position vector will be minus 1 1 and minus 2, okay. If we take the mod, it will be root 6, okay. Similarly, if we create the distance vector r minus r2, so mod of r minus r2, that is equal to r is equal to 0 1 comma 0 comma 1 minus 0 comma 4 comma minus 2, so that is equal to 1 comma minus 4 comma 3, that is equals to root 26. Now put the value, that is potential of the point r whose vector location is 1 comma 0 comma 1, that is equals to q1 4 pi epsilon naught r minus r1, put the value, okay, plus q2 4 pi epsilon naught r minus r2. So if you uh, 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 put the value of this q1 q2 4 pi epsilon naught and r minus r1, mod of r minus r1 and mod of r minus r2, then you get, after calculating, this value of the potential is approximately 5.8 minus 5.874 kilovolt, okay. So that is the uh, process how you calculate the potential difference with respect to one point, and with respect to one point which is situated in 1 comma 0 comma 1 vector location, to move to potential from infinite point to the vector location 2 comma minus 1 comma 3, whose charge is minus 4 microcoulomb, and another charge which is moved from infinite point to that point 0 comma 4 comma 2, whose charge is 5 microcoulomb. Okay, clear? Clear to all? Clear?
Yes, sir.
Okay. So you solve this equation, this problem. Okay. Practice problem 1. If a point charge, if a point charge 3 microcoulomb is located at origin. Located at origin means this point whose vector location is 0, 0, 0. Okay. In addition of two charge, which is situated, whose value is equal to 4 microcoulomb and 5 microcoulomb, located at a vector distance 2 comma minus 1 comma 3 and 0 comma 4 comma minus 2 respectively. Find the potential. Find the potential at the point at the point uh, minus 5 minus 1 5 and 2. Okay, and here you assume the infinite potential is equal to 0. Okay, calculate the potential at that point minus 1 5 and 2.
হ্যালো স্যার।
Yes.
স্যার বলছি আমি লিভ করছি স্যার।
কে বলছো?
হ্যালো।
At the origin. In addition, two of the point charge whose value is 4 microcoulomb and 5 microcoulomb, which are located at a position at a point vector. That means 4 minus 4 microcoulomb is situated at a position vector 2 minus 1 3, and 5 microcoulomb whose position vector is 0 4 minus 2 respectively, right? You have
Okay,
to
sir.
find the potential. You have to find the potential at point. Reference point is minus 1 5 and 2. Okay, assuming the vector, that means the infinite potential is equals to 0. Okay. Roll number 3, roll number 9, roll number 1, roll theory. In this uh, concept, okay, the Stokes theorem states that closed integral of, that means line integral of, closed line integral of dl, that is equals to del cross E dot ds. Del cross E dot ds. Now that is equals to 0. So we can write that close integral of E dot dl is equals to integration of del cross E, right? So if that is equals to 0, ds is not equal to 0 because ds is the differential area. So according, if we compare this equation, so del cross E is equals to 0. So this equation number 164, this equation number 164 and the equation number 163, that are the two important equations, okay, in the vector field. Okay, equation number 163 that specifies, that means closed integral of E dot dl is equals to 0 and del cross E is equals to 0. Okay, it is referred to as Maxwell equation. Okay, this is referred to as Maxwell equation. Remember it. Close integral of E dot dl. That means this specify the line integral of closed line integral of electric field intensity E. Okay, and curl of the electric field intensity E, that is equals to 0. And those two equations are referred to as Maxwell equation for the electrostatic field. Okay, these two equation is referred to as Maxwell equation of the electrostatic field, right? Okay, now the first equation, that means closed integral of E dot dl is equal to 0. This equation is called integral form of Maxwell equation of electrostatic field. Closed integral of E dot dl is equals to 0. That is called the integral form of Maxwell equation. Integral form of Maxwell equation of electrostatic field. And the second equation, that is del cross E is equal to 0. Del cross E is equal to 0. That means the curl of the electrostatic field intensity, okay, that is equals to 0. This equation is called differential form of Maxwell equation. So you have to remember these two forms, differential form as well as integral form of Maxwell equation. Okay, so first equation, that means closed integral of E dot dl is equals to 0. That is called the integral form of Maxwell equation, and del cross E is equals to 0. That is called differential form of the Maxwell equation. Okay, right? So you have to remember these two equations very carefully. Now, now we know that in the last class, the potential of any point in integral form, potential at any point in integral form, it is represented as minus of in E dot dl. Potential at integral, the V is equals to minus of E dot dl, right? Okay, minus of E dot dl. It is already proved in the earlier class. Okay, so it will be also if we take derivative or d differentiate this equation. So dv is equals to d and integration is cancel out. So dv is equals to minus of E dot dl, minus of E dot dl. So now this is this the E dot dl we can represent as minus of ex into dx minus of ey into dy minus of ez into dz in the Cartesian form. Okay, divergence, Cartesian form. Okay, so dv is represent as in Cartesian form E dot dl. It is the divergence of electrostatic field. Okay, that is minus of ex dx minus of ey dy and minus of ez dz, right? Okay, similarly, if we also know that dv is equals to, that means del v is equals to, del v is equals to, that means del v by del x into dx, del v by del y into dy, and del v by del y into dz. Okay, that means this del is represent a gradient. So if we compare equation number A and equation number B, right? If we compare the equation number A and equation number B, okay, so we get from this equation capital Ex, that means the magnitude component of the x direction of the electrostatic field E is equals to minus of del V by del x. Okay, then Ey, that is magnitude component of the electrostatic field in the y direction, that is E is equals to minus del V by del y, right? Okay, and Ez, that means the magnitude component of the electrostatic field of z direction, that is equals to minus of del V by del Z. So after comparing this equation, we can write from this equation, from this concept, that electrostatic field E is equals to del of V minus del of V, and this represent the gradient of the electric potential. Okay, so equation number 165 that gives the equation number 165 that gives that the electrostatic field intensity, that means E, electrostatic field intensity, that is E, is the gradient of the electrostatic potential V. That is one of the important equation of the Maxwell equation. Okay, electrostatic field E, electric field intensity E is the gradient of the electric potential V. So this is an important relation of E and V, and this gives another Maxwell equation. Okay, and why it is negative? The negative sign indicate specify that the direction of the electric field intensity, okay, the increasing direction of the electric field intensity, that is opposite to the direction of the electric potential increases, right? That specify the negative sign. And this equation number 165, this equation number 165 is a very important relation of electrostatic field intensity and the electrostatic potential V, and this is also called another Maxwell equations. Okay, okay, and the specifications of this equation 165b, that this equation is the another way of obtaining the electrostatic field intensity apart from Coulomb's law and Gauss law. Apart from Coulomb's law and Gauss law, right? So equation number 165, whose application, equation number 165, whose application is to create, is to generate or determine the electric field intensity with apart from Coulomb's law and Gauss law. That means by using this equation, if we know the electric potential, if we know the electric potential equation, then after taking the gradient of this electric potential, okay, we get the electric field intensity E. Okay, so that is the important relation between the electrostatic field intensity E and the electric potential, right? Okay, clear to, clear to, clear to all.
Yes, sir.
Okay, now let's give an example. Okay, তাহলে আমরা কি বুঝলাম, যে ইলেকট্রিক ফিল্ড ইন্টেন্সিটিটা আমরা বের করতে পারি যদি আমাদের ইলেকট্রিক পোটেনশিয়ালের ইকুয়েশনটা দেওয়া থাকে, বা ইলেকট্রিক পোটেনশিয়াল থেকে আমরা ইলেকট্রিক ফিল্ড ইন্টেন্সিটিটাকে ক্যালকুলেট করতে পারবো। দ্যাট ইজ দ্য রিলেশন অফ দ্য electric field intensity and the electric potential. Now by using this equation we can solve this problem. Okay, now there is an example given, V is equals to 10 r square sine theta cos phi, right? So this electric field is in the form of rho phi z, r theta phi, that means spherical coordinate. So this electric field V is in respect of spherical coordinate is given by 10 r square sine theta cos phi, right? Now, first we have to calculate the electric flux density D at the point 2 pi by 2 and 0. Okay, and let we calculate the work done of a moving 10 microcoulomb charge from a point A to point B. The point A whose location is 1, 30, 120 and B whose point location is 4, 90, 60. Right? That means both points are situated in spherical coordinate system. Here A is equals to 1, R is equals to 1, theta is equals to 30 degree and phi is equals to 120 degree. And B whose point location is R is equals to 4, theta is equals to 90 and phi is equals to 60. Right? Now, how we do the approach? So, electric flux density capital D, the import we have already know that electric flux density capital D is equals to epsilon naught into E, right? Epsilon naught into E, right? Now, E is equals to, if we apply this equation, this relation, okay, so E is equals to minus del V. Oh, we have the equation of electric potential V. So we take the gradient of this V. Okay. So del R of V AR 1 by R that, that is the gradient equation in the spherical coordinate. Remember it. Okay. Del R of V into AR plus 1 by R del theta of A theta plus 1 by R sin theta del V by del phi A phi. Right? Now, after taking the partial derivative of this equation, so we get capital E is equal to 20 by R cube sin theta cos phi AR minus 10 by R cube cos theta, okay, cos theta cos phi A theta plus 10 by R cube sin theta sin phi A phi. So that is the vector equation of the uh, E, right? Now, the electric field density, we have already know that the electric flux density E is equals to epsilon naught into E. Now, we have to calculate the electric flux density at the point 2, pi by 2, 2, pi by 2, 0. Now, if we put the value of 2, pi by 2, 0, so 2, pi by 2, 0 in this equation, okay, and the value will be electric flux density will be 2.5 epsilon naught R AR coulomb per meter square. Because the coulomb per meter square is the unit of the electric flux density. Okay, got my points? Now, okay, now the work done. Okay, now the work done will be W is equals to, according to first formula that is minus Q into A position to B position, A to B E dot dl, right? Okay, E dot dl. So that will be Q into VAB. That will be also, we know that Q into VAB. Okay, so W is equals to Q into potential at point B minus potential at point A, right? Okay, now Q into VB at potential, which point? This point B point whose vector location is 4, 90, 60, and A whose vector location is 1, 30, minus 120. Now put the value. Okay, so potential at point B at 4, 90, 60, and potential at A, that is 1, 30, 120. So we have already calculate the we have already know the equation of the V. Okay, now if we put the value, at that point in this equation, in this first equation, that is 10 r square by sin theta cos phi. Okay, so 10 by r square, that is 10 by 16 sine 90, okay, cos 60, sine 91 cos 60 half. Similarly, that is 1 comma 30 1 comma 30 comma minus 120. So 10 by 1 sine 30 cos 20. So sine 30 is equal to half, cos 30, 120 is equal to minus half. So after calculating this, okay, we get the work done. We get the work done, that is 28.125 microjoule. Okay, so that is the work done of moving a point, a 10 coulomb charge, okay, from A point to B point, but it is in spherical region. Okay, that is the uh, another example. When we apply this relation, E is equals to minus of del V, and you have to remember that the electric field intensity E, that is equals to divergence of electric potential. Remember it, very important lesson. Electric field intensity is the gradient, not divergence, sorry, gradient of the electric potential. Okay, that is the important relation of electric potential and electric field intensity. Clear?
Sir, can you scroll down once, please?
Which one?
Sir, the work done, work done.
Problem.
B.
Okay.
Sir, here from the second step, how did you like, how third step from I understand, sir.
This one.
No, sir. After that, after that.
Which one?
Yes, sir. From that to the next step.
This one.
Yes, sir. From that base.
What is the equation of V? What is the equation of electric potential? The equation of the electric potential already given. V is equals to 10 r square sine theta cos phi. Okay, that is the equation of the electric potential. So when we calculate the electric potential at point A, whose value r is equals to 1, theta is equal to 30, and phi is equal to 120. If we put the value of r theta phi of this equation, we get the electric potential at point A. And if you put r is equals to 4, theta is equals to 90, and phi is equals to 60 at this equation, we get the electric potential at point B. That is that. Okay. কি বুঝছো? হ্যালো।
Sir, yes, sir. Yes, sir.
হুম। সো এইটা এই রিলেশনসটা খুব ইম্পর্টেন্ট রিলেশন। এই রিলেশনসটাকে অ্যাপ্লাই করে তোমাকে অনেক প্রবলেম সলিউশন করতে হবে। ওকে, দিস রিলেশন, ওকে, দিস রিলেশন ইজ আ ভেরি ইম্পর্টেন্ট রিলেশন। আচ্ছা, তোমরা এই প্রবলেমটা একটু নিয়ে নাও। এই প্রবলেমটা একটু আমাকে করে, আজকে এখন টাইম নেই আর, হয়তো নিয়ে নেই, তো এই প্রবলেমটা একটু নিয়ে নাও। এই প্রবলেমটা করে আমাকে পাঠাবে। প্র্যাকটিস প্রবলেম 1, given that E is equals to 3x square plus yax plus x into ay kilovolt per meter. Find the work done in moving minus 2 microcoulomb charge from a vector location 0, 5, 0, 5, 0 to -2, -1, 0 by taking the path। কোন পাথে যাচ্ছে? 0, 0, 5, 0 থেকে যাচ্ছে 2, 5, 0, সেখান থেকে যাচ্ছে আবার 2, -1, 0। ওকে, বা সেকেন্ড যেতে পারবে along the path y is equals to 5, 3x, মানে এটা একটা স্ট্রেট লাইন ইকুয়েশন। এই স্ট্রেট লাইন ইকুয়েশনে যদি যাই তাহলে এর ওয়ার্ক ডানটা বের করো, বা এটা বি পার্ট। আর যদি এই পাথে যাই তাহলে তার ওয়ার্ক ডানটা বের করতে হবে তোমাকে, যেখানে ইলেকট্রিক ফিল্ড ইন্টেন্সিটি যেটা ই তোমার দেওয়া আছে। ওকে, আর কিউ যেটা আছে, যেটা তুমি মুভ করাচ্ছ চার্জটা, তার ভ্যালু হচ্ছে তোমার 2 মাইক্রোকুলম। ঠিক আছে, এই এই প্রবলেমটা একটু নিয়ে নাও, এই প্রবলেমটা একটু নিয়ে নাও, এটা করে আমাকে পাঠাবে। ওকে, এই চ্যাপ্টারটা আমার শেষ হয়ে গেল, আর তোমাদের দুটো চ্যাপ্টার বাকি। ঠিক আছে, অলরেডি 4টে চ্যাপ্টার হয়ে গেল, দুটো চ্যাপ্টার বাকি। একটা হচ্ছে ম্যাগনেটিক বাউন্ডারি কন্ডিশনের চ্যাপ্টার আছে একটা, আর হচ্ছে ম্যাগনেটোস্ট্যাটিক ফিল্ড আছে। ইলেকট্রোস্ট্যাটিক ফিল্ডটা কমপ্লিট। ঠিক আছে, শুধু একটা জিনিস বাকি রইলো, ওটা নেক্সট দিন করাবো, তাহলে কমপ্লিট হয়ে যায়। ইলেকট্রিক ডাইপোল মোমেন্ট, ইলেকট্রিক ডাইপোল এন্ড ফ্লাক্স লাইন, এটা হলেই হয়ে যাবে। শুভম, ঠিক আছে। ঠিক আছে শুভম, ওকে, অলরাইট শুভম, ঠিক আছে, তোমার প্রবলেম। Any doubts, anyone? Any doubts, anyone? Okay. ক্লাস এন্ড করছি আমি, হ্যাঁ।